Hello, this is Pointing Arrows by Arbitrary. Another 9x9 Sudoku with a pretty interesting rule set. So let's look at the rules of this puzzle. Normal Sudoku rules apply, so 1 to 9 in every row, column, and 3x3 box. Pointer arrows, so these arrows here. Digits along arrows must sum to the value in the connected circle. So these digits along an arrow must sum to the value in the circle. So if this was a 1 and a 4, this would then have to be a 5. This cell would then be that cell. So this cell sums to this cell, so they're just equal. And so on and so forth. Now what else do we have? The arrow tips point towards a cell containing the digit within the arrow's circle. So whatever the circle is, let's say this was a 2, sorry, not a 2, a 3, then the arrow must point to a 3 somewhere in this direction. Maybe it's here. But there is an additional constraint. Not only must it point to that digit, the value in the arrow tip, so say this was a 2, indicates the distance from the arrow tip to this cell. So if this was a 2, then the 3 that it's pointing to must be 2 cells away. So I would assume a 3 is there. Yeah, that's what that is what I believe it is. If I want to check here, you can't really see it, but yep, that is correct. So something like this would work. So yes. There may be other instances of the same digit between this cell and the arrow tip. So a 3 here and a 2 here puts a 3 here, but that doesn't mean that this can't be a 3. It could also be a 3, as long as this 2 sees a 3 2 cells away from it in this direction. So those are the rules of this puzzle, and with that, let us begin solving. There are a lot of these single arrows here, which really imply that these two are the same digit. And really what it implies is that this number must be here, which then must be seen some number of cells away. So if this was like, say, a 2 and this was a 2, then this must be 2 cells away. So what that would then mean is that for these 1 cell arrows, whatever number is here must also be the number of cells away from the tip. And I immediately see that for certain arrows, we're actually pointing very close to the edge of the puzzle. So this actually can only see 2 cells. It can only see something 1 away and 2 away, meaning that this value can really only be 1 or 2, and similarly that must definitely be 1 or 2. This I think is even more constrained, yes, because it can only see 2 cells away. However, it can't see this cell. So this can't be a 1, because it would then see this cell, which would have to be the same as it. Right? This 1 would mean this is a 1, and therefore 1 cell away, it would see another 1, which doesn't work because of Sudoku. So this actually can't be a 1, and therefore must be a 2, which then sees a 2 cells away. That must then be a 1, which then sees 1 cell away. Cool. This is actually also constrained by this 1 and this 2, because this cell only can see things in 3 possible cells. However, because of this 1 and this 2, we really only know that this can be a 3, because it can't be a 1 or a 2. So it must be a 3, and must see a 3 cells away. We have something similar here and here, I think. Yeah. In fact, because this sees 2 possible cells, then this must be only a 1 or a 2. And similarly, this is actually identical to this arrow because it can't see a 1, otherwise you put a 1 here along with a 1 here. So it must therefore be a 2, which sees a 2 here. This is therefore a 1, which sees a 1 here. Okay, that is decent. We do have 2 other single arrows though, but they're pretty far away from the edges of the board. So I guess it doesn't really say much. I think we could probably do Sudoku. Yeah, because in this box, where does the 1 go? These 4 1s, look at it and make a 1 go here. We don't know where the 1 goes in a lot of cells. The 1s can be here and here. Okay, what about 2s? Yeah, these 4 2s, then put a 2 in here. Anywhere else? Yes, in this box, 2 must go in here, owing to these 4 2s. And therefore in the center, that 2 must be there. So that's all the 2s we can place. Okay, that's pretty good. I see. This cell is a bit interesting because there are only 3 possible things it can see, or it can only see 3 possible distances away, 1, 2, or 3. But because of these 2 cells, it can't be a 1 or 2, so it must be a 3, which therefore sees this cell. But we know this isn't a 3 because it is actually the same as this cell, so it's actually not a 3, but we do know these 2 cells are the same. And this is 3 plus this cell, which we don't know. Could very well be a 1, I think. Could be anything else as well. Yeah, it could be anything from like a 1 to a 6. Okay. Let's see this one. This actually can't be a 1, 2, or 3. That is interesting because what can it see? It can only see 4 things. So this can't be a 1, 2, or 3 and therefore must be a 4, which then sees a 4 cells away. That is cool. That is cool. Yeah, okay. This cell maybe? I mean, this cell is also decently interesting, but not entirely. This cell can see 4 things, but it can't be a 1 or a 2. It could be a 3 or a 4 though. But it can't be a 3. That's it. It can't be a 3 because it would see a 2, which then places a 2 in here. But obviously if you already have 3 on the arrow, these 2 digits cannot sum to a 2. So this can't be a 3 then. It must be a 4, which makes this cell the one that's seen, which then has to be the same as that. So we'll color those in. I think we can do something similar to this, although this is really not constrained. This can be, well, it sees 6 things, so it can be from 1 to 6, but it can't be a 1 or 2. So tentatively our options are 3, 4, 5, and 6. We can in fact remove 6 though, because a 6 would see a 1, therefore placing a 1 here, so it doesn't work. But it could be a lot of other things. It could be 3, 4, and 5. It could be that one, because that would place a pink here, which I think is fine. Alright, these 2 4s see these cells, so that's a 4. So that can't be a 4. Meaning that, 1, 2... So this one sees either this cell or that cell. We can't make too many deductions from that though. Well, yes, in this box, the 3, where does it go? The 3 can't go there, and this actually can't be 3 because we know the 3 would then go here, and 4 plus something can't add up to 3. So 3 is in one of these 2 cells, which hopefully sees something. Yep, it sees these cells. This 3 sees these cells. And 3 can't be here because that will put a 3 there, which doesn't work. You can't have 3 and some positive integer add up to 3. So 3 is just there. That helps us because that's a 7 and that's also a 7. Therefore 7 goes in one of those cells, but 7 can't go in here because that would put a 7 there. So this is a 7. This sees 5 things. I think we can finally start looking at that. So this sees 5 things. It can't be a 1 because a 1 is already there. It can't be a 4 because a 4 would go there. It can't be a 2 or 3 either because the second and third positions are 4s, and whatever is here is also there. So you can't have a 2 here and then a 4 here, which is what this sees. So this can't be a 1, 2, 3, or 4, meaning it must just be a 5, which then sees 5 cells away. In this box then, the 5s see everything but that, and therefore 5's in one of these cells. Here we need a 6, 8, and 9. Therefore we can place a 6 or 9 here following the orange, but we now know that can't be a 6 because that will force 2 3's in the same box. Because it's either 8 or a 9, this must then be a 5 or a 6, but it clearly can't be a 5 because of the 5 already present in the column. So it must then be 6, making this a 9. So that's a 6, 8 pair. The remaining cells here are then 7 and 9, which we can't resolve just yet. The remaining cells here though are 5, 6, 8, which also can't really be resolved. Wow. Remaining cells here are 7 and 8, but we don't know which ones they are. Okay. I guess, this can't be a 5 then, because a 5 here would look at this cell, which then puts a 7 here. It puts a 7 there. But we already have a 5 and a 7 here, so that must then be a 2, which clashes with this 2. So this can't be a 5, that's a 3, which sees this cell. So those are the same. I'll make them green. This 3 removes that, so that's a 3. Remaining are 6, 8, and 9. And that can't be a 9. So that is a 3. That is a 3 in the corner. Nice. I've seen a lot of 3s in the corner as well. These 3s see a 3, force a 3 into that cell. Remaining cells in this column are therefore 5, 6, and 8, which we still have no way of disambiguating. A 1 must exist in this box, which are seen by the 1s there to force a 1 in here. Remaining cells are therefore 5, 7, and 8. This can't be a 5, and I guess we can remove the 5 pencil marks. Oh, the 7 here sees both of those, so those can't be 7s. That's therefore a 7. What else do we have? Well, that's a 5, 6, or 8, but it can't be a 5, so that's a 6 or 8. Which helps because that forms a 6, 8 pair here, forcing that to be a 9. Okay, I guess we can start considering... No, we look at the rest of this column first. Those have to be 4 and 7, which... Oh, it still isn't resolved, wow. Okay. I guess we could try... just more Sudoku. Yeah. Oh, that is... Wait, no, does that break? No, that doesn't break. I thought it broke. These two 4s sees a 4 in these cells, and that can't be a 4. Now, can this green cell be a 4? It can't, because it would then be here, which forces a 1 here to clash with that. So that can't be a 4, therefore that must be a 4. That's a 7. Oh, that scared me. I thought we broke the puzzle there. Okay. These are 5, 7, 8, 9. These are 4, 6, and 8. That can't be a 4, it can't be an 8 by this pair. Sorry, this pair, so that's a 6. That's an 8, and that is a 4. This is all resolved. That's a 6, 8, 6. These cells are 8 and 9, which is resolved by this 9. So 8, 9. Does it help here? Probably. No, not really. Wow. I guess we can look at these, which must be a 1, which has to go there because of this one. And an 8, which is there. This cell is just a single digit, as a 9. I guess 8 removes 8 from that. These have to be 4, 7, 4, 6, 7. That can't be a 4, that can't be a 7, but otherwise unresolved. These must be... Oh, sorry, we are seeing that as well. So 4, 6, 7, 8. 4, 6, 7, 8. But we did remember that this can't be a 4. 7 and 8 here removes that, so that just has to be a 6, meaning that's a 9. Forcing a 9 there. We can remove 6 from these cells. But more importantly, I guess 4 from this cell as well, and from that cell, which actually forces a 4 there. That resolves this triple. That does not resolve, but this 9 helps. That helps, that make a 7, 9 there. These are 5, 8, 5, 7, 8, which is good. This 7 and 8, let's make that a 5. That's an 8, 5. That is a 7. That can't be a 5 anymore because that's a 6 and an 8. That makes sense. This 6 means that's an 8. That's a 6. That is an 8, resolving somewhat. 5, 6 pair here forces that to be an 8. This 8 means that's a 7. That's an 8. These two cells are 4 and 5, which we can resolve. 5 here, 4 there. That makes this a 6, which resolves this, and we have 2 cells remaining, which are 5, which has to be there, and 9, which has to be there. Solving the puzzle. So that was nice. That was a really interesting rule set. It appears that there is, in fact, another puzzle of a higher difficulty with the same rule set, so I might try that. But until then, I hope you enjoyed watching. I'll see you. Bye bye.